Hello, everyone, and welcome to Africa Fire Mission's weekly virtual training session. My name is Mike, and I'm the programs director here at Africa Fire Mission. We're so happy that you took time out of your schedules to join us for today's virtual training session. This week, we're joined again by Mark Feyst. He's a fire chief, fire instructor, who's worked with us for a couple years now, done a lot of our virtual trainings as well as some in-person training in Kenya. And he's here today to continue sort of part two of last week's training about fire dynamics. If you haven't seen that, you can catch up with us later on by checking out our YouTube channel. Just search for Africa Fire Mission on YouTube. While you're there, click subscribe and you'll be able to keep up with everything that's going on with Africa Fire Mission, as well as checking out all of our other social media, Facebook, TikTok, and all those others. Before we get started with today's training, I'm going to pass things over to Jose, who's Africa Fire Mission's fire safety officer. He's going to get us going here with a couple words of encouragement.
Thank you so much, Mike, and thanks, Mark, for always being here again, and you that has found time and bundles to show up. Thank you very much. We don't take that for granted. Today I have a stress ball. I'm having a stress ball. I'm stressed. And it is okay to be stressed. Yeah, but how you react after the stress, that is actually what matters. You should actually sit down, sit back, take a deep breath, and tell yourself, how should I react after this? And this stress is actually through one of my cousins who passed on, and we just, what we call it, we buried him yesterday. And it kept on thinking, wow, such a young life to be taken. And all of a sudden, what am I here for? You know, you start getting these questions of, am I next? You know, you're fearful, you're feeling uncomfortable and all that stuff. You are not alone. I've been talking to my colleagues a few minutes ago and even sharing my stress levels. Yeah, it is okay to be vulnerable. It is okay to feel like you're out of breath, but hey, how you react after that is what matters. Get something that helps you. Well, I wouldn't recommend alcohol. That will actually mess you more. But then get something like a stress ball, you know? Get some tools that can help you to actually relieve that stress. Because after you react from what you're going through, that is actually what will define the next steps. So I wish you well, and I wish you that you don't bottle everything up inside of you. Please be vulnerable to your colleagues, be vulnerable to your friends, your family, and be vulnerable to your brothers and sisters in the firehouse. From there, you will find help. Thank you very much. Back to you, Chief Mike.
All righty. Thank you, Jose. We always appreciate you sharing those words of encouragement and all the other work that you do to support firefighters, really, from throughout all of Africa. Before we get started, let me just touch on a couple of administrative notes. Stick around for at least 70% of today's training, which is usually about 40 or 45 minutes. We'll get you that certificate of attendance for today's training. Keep an eye on the chat if you get cut off or you can't stick around for the whole training. I'll drop a link in here that'll show you where you can watch the training, answer a couple questions, and earn that certificate of attendance. So please check out our webpage, www.africafiremission.org, and go to the resources tab. Under the training materials, there's a whole bunch of good stuff. We have lots of free resources there. So I encourage you to take advantage of those when you can. At this point in time, I'm going to pass things over to Mark to get us started with today's training.
All right. Thank you, Mike. Thank you, Jose, and everybody. Welcome. Good afternoon. Thanks for joining us once again for another weekly session of training. And good to see all of you with your faces there on on the Zoom bar here, like Godric and Kingsley. Good to see you folks again. So we're going to continue from last week. Last week I was parachuted in to fill in last minute, and it kind of kicked off the fire dynamics side of it in terms of your monthly look at the topic of fire dynamics. And we're going to continue that today with looking at nozzles and fire flows or water delivery in terms of what's best and what should we be considering to be the best when delivering water to suppress our fires. Before we get into our lesson, as you can tell, I am in uniform, so I am working. I'm at the station today again, so hopefully no calls will come in to interrupt us. If it's a serious call, I will have to go, but again, hopefully that won't happen in the next hour. But right at our session end, when our session does end, I'm going to have to leave right away. I have a meeting at 10 o'clock in the morning, my time, to meet with a future person that we're hiring here in our department. So I won't be able to stay and hang around with you folks. All right. So let's get into our topic at hand. I'm going to share my screen. Okay, let's get this going here. All right. So, as I mentioned, we're building on from last week. And last week, we laid some foundational knowledge in terms of fires and fire dynamics, some key terms like heat release rates, heat flux. We looked at some measurements like megawatts. We looked at a fancy word called pyrolysis and the breaking down of materials that contribute to what we call black fire or the smoke of the fire. And that was discussed because it's important for us to understand those foundational terms because as you look at the next phase today, which is water delivery and how water works on fire, you're going to get a better understanding, and the connection can be made between the two. Even though my title slide is called Tactical Firefighter Notes, it's going to be looking at water delivery and what type of water, or how big water should be in suppressing fire. Let's just look at the two pictures that we have in front of you. Okay, we have two pictures that are vastly different from each other. And even though the building construction type differs a little bit from where you might be in your part of the world, be it Kenya, Africa, India, Saudi Arabia, it may differ a bit. But as I mentioned last week, fire is the same. That's one of the common denominators that we can underline and tuck in our back pocket. No matter where we go in this world, fire is the same. It will burn the same, it will kill the same, it will behave the same, and it is extinguished in the same way. And in our two pictures, let's look at the one on the bottom first. The one on the bottom shows a bunch of firefighters going in with the hand line, and you can look at the smoke that is leaving the structure. Okay, that smoke is in color. If you can see it on your screen, that smoke in color is very dirty and brown. And when we look at smoke like that, we can tell that there is a lot of heat for one thing. We can't see the movement, so it's a still picture. We can't see the movement, but it's probably moving quite quickly, which has a lot of velocity, so a lot of heat is inside that building. There's a lot of heat exhausting or leaving the building, as it were. But that color smoke tells us that the fire is burning, in this case, in the wood structure. And when it's brown like that, it means I actually have wood combined with other products that are in the home or in that building that are starting to combust, starting to break down, starting to ignite. And this is the beginning phase of that development going from ignition to growth up to the flashover and then later on the fully developed phase. You'll notice in that picture that the smoke leaving is towards the top half of the door, and with a firefighter going in the bottom half there, it's kind of clear. And we need to again understand that what we have here is another term that you need to be aware of in looking at how we combat fire, how we suppress fire. That's a bilateral flow path. That means there's two directions of movement. On the top half, you have the smoke and the heat exhausting, and the bottom is that cool air coming in to fuel the fire. So the fire itself needs to breathe. It needs air to survive, and it needs air to do its job, just like you need air to breathe and live and to do your job. And so the fire is drawing that air in, and it's being drawn in through the bottom, and that's what's helping to feed. And eventually, if we do not do something with our hose line, so that hose line is being brought in, if we do not do something, and I say do something in terms of applying water to cool off the environment. So again, think back to last week. I discussed radiant heat transfer. Radiant heat is the heat that's found within that smoke within the fire that is transferring from the fire itself to other objects in the room through the means of convection, conduction, or by radiant transfer. When radiant heat, which is the primary method of fire or heat transfer in a fire setting, when radiant heat is not cooled, when we don't stop that heat transfer by cooling the environment, the smoke you see in that picture eventually becomes the picture in the top right-hand corner, which is now going to be a big ball of fire. So we see two examples. We see the beginning of what smoke looks like, of the products of combustion. We see the beginning phases of heat transfer occurring, and then we see in the second picture, the top corner of the slide here, we see the end result of when you have your fuel, your heat, and air sufficient enough to combine together, you have the finished product of flaming combustion. And I mentioned that term last week. There's flaming and non-flaming. The picture in the top right-hand corner is an example of flaming combustion. The picture in the bottom left-hand corner is an example of non-flaming combustion. There's no fire yet, but there's still combustion taking place. There's still heat and there's still fuel. It's just missing that one ingredient of air. Okay, here's 5 ways that water helps us to gain or helps us to extinguish fire. Right? So if you want to take anything down, these 5 points would be the key things to kind of take away from today. Because as I mentioned last week, water is what we need. Water is what's used. Water is that key common denominator for extinguishing fire. So the one way that water helps us to extinguish fire is by the unaffected fuel. That is the fuel that is in that structure that's there ready to burn. So let's give an example. In a residential building, you may have multiple rooms on the one floor. If the fire is in the one room, the other rooms are that unaffected fuel. That is fuel load of contents, bedding, paint on the walls. That's all fuel load ready to burn. So the water helps us to cool it off and to keep it cool so that it doesn't become part of the fuel load that's igniting and contributing to the fire. So it helps us to deal with the unaffected fuel. The second method is by fuel surfaces. So it helps us to actually cool what is actually burning. And that's where we look back last week, our heat release rates, the megawatts, the energy production of fire. That is the fuel surfaces, the floor, the ceiling, the walls, the furnishing itself. We are able to use water to cool it off and drop that temperature down drastically. It, of course, is going to help us to extinguish the actual fire itself. it's going to fourthly help us deal with what I mentioned, the term black fire, that hot smoke. So think back to this picture here in the top right hand corner, that black smoke coming off of the flame, that's black fire. So before the flame is actually visible, you're going to see some really turbulent, dark, thick black smoke. That's black fire. Our water, when we actually put water on that black fire into that smoke itself, helps to cool off and drop that temperature. And then lastly, the hot surfaces, as I mentioned, the ceiling, floors, and walls, that's going to be also cooled drastically as well. So those are the 5 ways that water helps us to gain the upper hand and to assist with extinguishing and suppressing fire. When looking at water delivery, when I'm looking at fire flow, water flows and fire flows, and how much water should I be delivering and should I be pumping out of my nozzle to dump on that fire, I want to dump a lot. So think of a 55-gallon drum or 200 and I think 7-liter drum. That's a big drum. It's a big container. If I fill that full of water and I dump it on top of the fire, that's what I want. I want a lot of water that's being dumped like a deluge. And I'm looking at what trucks I'm bringing, the hand lines and the hose lines, the branches, the nozzles that I'm using to deliver water. I want to make sure I am delivering a ton or a lot of water. I want 55-gallon drums of water being delivered out of my nozzle or out of my branch every minute. So that way I know that when I dump water on it, I am dropping the temperature immediately and I am having a good effect to stop things as opposed to things getting worse. So in looking at delivering water, you always got to consider the one thing of nozzle reaction. So you have to look at what you're using. You have to look at the hose lines, the branches that you have at your disposal on your trucks when they're flowing water at the proper flow rate of liters per minute, gallons per minute, PSI or kilopascals, kPa, how much force is being produced back on me. And what we want to try and accomplish, excuse me, is we want to try and accomplish a reactionary force of no more than 69 pounds for one firefighter to handle that hose line or that branch. Why only one firefighter? Well, because we are looking at a common problem in the fire service, and that is staffing limitations, a lack of firefighters to do the job. There's only so many showing up, but there's a lot of work that has to get done. And so with one firefighter on a hose line or on a branch, they're able to do a lot. They can deliver a lot of water. They can initiate an interior fire attack, and we don't want that hose line or that branch to overpower them so that they cannot do their job. We want them to be able to do their job and to have control over that hose or over that nozzle and that branch. And that is going to be at 69 pounds or less. So if we have a nozzle reaction being produced of only 55 pounds, great. If we're at 62, not a problem. But once I go above that number of 69, if I have 74 pounds of nozzle reaction working back against me, it's going to start to overtake me. That means I'm no longer able to control that hose line and be effective in my job. How will you know how much nozzle reaction is being produced? And the answer is this. Take your hose lines or your branches, go out somewhere, flow them at the proper pressure and the proper flow rate, and you can use a scale like a fish scale or a weigh scale for weighing suitcases. And if you tie the branch to that scale to a static secure spot, you'll see how much when the water's flowing out from the nozzle, you'll see how much force is being pulled back, and on that scale should tell you what that is, 50 pounds, 55 pounds, 69 pounds, or whatever it might be. That's how you're going to know. You're only going to know by actually getting out there and doing it. When we look at different nozzle pressures, right? So different nozzles require different pressures to operate. So you have 50-pound PSI, which is like 350 kPa. You have 75-pound PSI, which is uh, 5 something kPa, or have 100-pound PSI, which is 700 kPa. Those are all the pressures required to make those nozzles work. What you're seeing in this chart is you're seeing the nozzle reaction that's created with those nozzle pressures and the amount of water flowing. Obviously, as you increase your water flow, you're going to increase nozzle reaction. That's just basic science and basic law of Newton's law of physics. When you increase the pressure required to make that nozzle work, you are also increasing nozzle reaction as well. So something to consider. When you look at what nozzles you have that you're using, are they working against us or are they working for us? And the higher the nozzle pressure and the more water flow I'm producing, it's working against me. I need more people to staff that line to make it work properly. The second thing I want to point out is kinks. Kinks are where the hose itself bends. All right, the branch is meant to stay straight as much as possible. That means the water can flow through that laminar opening with ease. But when I have a bend in the hose somewhere, like you see in the picture, the hose is caught under the tire a little bit. That's a kink, and kinks are not good because this chart, just a real quick review of this chart. This chart is showing you how much water flow you're losing just from one kink. Okay, let's just look at the first line where I'm showing one type of nozzle that's flowing 150 GPMs, that's gallons per minute, and the nozzle itself is meant to work at 75 pounds. The rated flow means what it can deliver is 150 GPMs. When I have one kink in that hose line with that particular nozzle, you can see that I'm dropping down to 118 GPM. So I'm losing about 11% um, of my water flow that's needed. Why is the number 150 being used? It's because that's what's recommended by NFPA for if I'm doing any interior residential structure fire attack, I have to have 150 GPMs flowing minimum from my hand line, let alone having two for a combined fire flow of 300 GPMs. That's for a residential building. If I'm going into a commercial building or an industrial building or like a shopping mall, I have to have a lot more. I have to have much more than 150. It's going to be in the 250 GPM range that I am recommended to have to combat that fire load and that fuel load within those buildings. The rest of the numbers you see below are just showing different examples of different types of nozzles and hose lines based on nozzle pressure and flow rates, but you're seeing there's a reduction. There's always going to be a reduction of water flow. And we do not want to have a reduction of water flow because kinks kill. A kink in the hand line kills firefighters. How? Because I'm losing my water. What's my defense against the fire? It's putting water on it. I want to dump, like I said, those 55-gallon drums of water on that fire every minute. But when I have a kink in my hand line, I'm not able to dump 55 gallons of water. I'm only able to dump this little cup of water, and that's it. And that little cup of water is not enough to put the fire out. Hence, the fire overtakes us and either destroys the building and we get trapped, which means we die in the process, or we get severely injured in the process as well. And that's why I'm saying to you, kinks do kill as far as the fire service is concerned. So when you're looking at fire flows, delivering water, you want to make sure you never have kinks in the hand line. One thing I want to say here, and it's important for us to understand, and that is even though we have branches, we have nozzles, we have hoses, we have trucks with water, we have water sources, a nozzle does not produce water. A nozzle only delivers water. What produces water are the sources of water, lakes, rivers, pools, hydrants. That's what produces water. We have to get access to that. And if we get access to it, we can deliver that water to the nozzle that's needed to dump water on that particular fire. So we can't expect the nozzle to produce what's needed. We have to make sure we have it and we secure it and deliver it. Let's look at time versus temperature because it's very important for us to understand when I want to dump water, when I want to deliver water onto fire, we have to understand what kind of temperatures am I dealing with. Now, this chart you're looking at is based on scientific research here in North America, and it's looking at residential buildings. Again, residential, not commercial, not industrial. And what we're seeing here is a very realistic picture of what we're facing. The two colors that you want to focus on are the green and the blues. The green and the blue. The blue is going to be my ceiling temperature, and the green is my available air that I have to use. The very bottom is showing me my time. So as I am starting my fire attack, and in the minutes, that's the time factor, and the upright portion of the chart is showing me my temperature. If you look at within the first 5 minutes of fire growth and development, you see that blue line? There's a sharp spike, and the temperature is well above 1,000 degrees Fahrenheit. Everything I have here is in imperial, unfortunately, not Celsius, but um, it's 1,000 degrees Fahrenheit. And then you have a dropping. You see that blue line drops. And at the same time, the green, which is very high, it gets drawn down with the blue because the fire, as it grows, is eating up using all the available air in that room. That's why there's a big drop in the air as the blue temperature is increasing. Then around the 10-minute mark, we see a sharp spike again. Okay, that sharp spike is where available air has now come in, has been introduced, and that fire that's in non-combustion phase, so there's no flame, but there's heat, there's fuel, it's just missing the air. As that air is introduced, you see how exponentially that temperature increases. It goes from roughly 400 degrees Fahrenheit and it goes up to almost 2,000 degrees Fahrenheit. Why am I showing you this? You have to look at the response time of what you are responding in to a residential fire. At what point do you show up on the fire ground? Are you coming in at the 5-minute mark, the 10-minute mark, the 12-minute mark, the 15-minute mark? Because that's what you're facing. You're facing temperatures of anywhere from 1,000 plus to 2,000 degrees Fahrenheit in that arrival window. Why is that important for me to know? With that extreme heat requires a lot of water to bring that temperature down to where it's got to be, which is around 0. That's where I want to go with this. And that's why I want to show you this visual is that you want to make sure the water you're flowing, the water you are pumping and delivering to your nozzle through your branch is enough to take that temperature from 2,000 degrees right down to almost 0. That's what I'm trying to accomplish. Okay, so I mentioned the word flashover, and we looked at last week some terms, measurement like kilowatts, megawatts. Um, the number to remember for what trigger point does flashover occur at the ceiling, and that's at the ceiling, that's not at the floor, so at the ceiling is 1112 degrees Fahrenheit. That's the trigger point. Once that ceiling has hit that temperature area and the floor has that radiant heat transferring to the floor, and it shows you that 20 kilowatts per meter squared. Once those two are present and they combine, that's when flashover occurs. What do I need to produce a flashover? As it says here, I just need 1 megawatt to produce that environment of energy production. Well, what does that look like? Well, here's some examples. I mentioned this last week, just a quick review. Some examples of what we see here for different energy production. Waste paper basket, your sofa chair, your love seat, your bed, and they're all producing different megawatts of energy production. But it only takes one sofa chair in one empty room, which is 2 megawatts of energy production to produce that flashover within that residential space. So not a whole lot's needed. And a lot of rooms, a lot of homes, a lot of buildings have more than just that stuffed and crammed in there. A lot of fuel load, a lot of energy production is being produced from what's inside there. So now we know what we're facing. Let's look at how my water streams, the type of stream, and the amount of water, what does that do for me? Because it can do one of two things. It can either help me or it can make things worse. So this smart guy in New Zealand, Cliff, he's a fire protection engineer, did some research, and he found that when you have a ceiling temperature of 1112 degrees Fahrenheit, that a fog, which is a wide pattern of water, absorbs heat at 75% efficiency. So when we look at that statement, we think, wow, that's good. That's absorbing a lot of heat compared to the term smoothbore or a straight stream only absorbs 50% of the heat. So looking at 75 or 50, you would think, hey, I got a bigger number. So therefore, that water stream, that fog pattern is absorbing more heat. It's doing me a good thing. But we got to stop and think for a second. What actually is happening when I introduce a fog pattern into a superheated area at 1,000 to 2,000 degrees Fahrenheit? Is it really absorbing heat? And the answer is no. It's actually doing us harm. It's absorbing heat, but it's absorbing heat and turning it into steam. And that's where the harm comes in. Steam, or I back up water expands into steam at 1,700 times its original volume. So I take one drop of water, it's one drop, and if I heat that up to boiling point, that water becomes a vapor, or it becomes steam. And that steam will become 1,700 times the volume of that one water droplet. That's at the boiling point. Water boils at 212 degrees Fahrenheit. We're dealing with a structure fire at a residence, which means that, as you see in my temperature graphs, I am between 1,000 and 2,000 degrees Fahrenheit, not 212 degrees Fahrenheit. And so when we're looking at 1,000 degrees of heat, that steam conversion goes from 1,700 times, it now increases to 4,200 times its original volume. That means that one little drop of water, when I throw that drop into a 1,000-degree Fahrenheit environment, turns to steam immediately, and expands 4,200 times its original volume. So you think, okay, no big deal. One little water droplet. But how many water droplets are in that fog pattern that's being dispersed into that superheated environment? Multiple water droplets. And each one is expanding 4,200 times its original volume, becoming steam. And steam burns. Steam does not feel good. When you get steam burned as a firefighter, you are going to feel it. You're going to feel it in your boots. You're going to feel it through your gloves. You're going to feel it through your helmet, on your head. It burns. It can burn right through the gear and give you third-degree burns, let alone the occupants within that structure. They're also getting burned as well. So even though that sentence, that research finding from Cliff Barnett shows that the fog stream absorbs a lot of heat, that's not what I want. I want the straight stream, which absorbs half that amount because it does not turn to as much steam, as I'm going to show you with a few more points here. When looking at my water stream, so you look at your nozzle, the water that comes out from your nozzle is traveling. I want that stream reach to do some good for me. And a fog pattern with little water droplets doesn't have the reach that a straight stream will give me. A straight stream, I might get 20 feet, which might be like 4 meters of reach. Whereas a fog pattern, I'm only going to get maybe 3, 4, or 5 feet, maybe one to 1.5 meters of actual reach. That's not very far. And then you factor in if it's a windy day, if it's a lot of wind that's being produced, that wind carries my little water droplets away. Whereas if I have a straight stream, which has bigger, fatter water droplets, they're more prone to actually make it to the fire and not be carried away by the wind. Okay, so a straight stream in terms of water flow, fire flows, what type of stream pattern should I have? I want straight. So that way I'm guaranteeing it's actually going to reach its target. It's going to produce less steam. And that way I'm not, as a firefighter, going to hurt myself in the process with that steam conversion factor. All right, so I mentioned water droplets. And this is kind of the culmination of the crux of our topic here today, right? Fire flows, water delivery. What kind of water do I want to have being dumped on my fire? And I use the analogy of a 55-gallon drum, but in reality, I can't carry a 55-gallon drum and dump it. So I got to use my nozzle. So a nozzle is delivering water. When the water leaves the nozzle, and I've seen what kind of nozzles you guys use. So you have a combination, which gives you the opportunity to go to a fog pattern or a straight stream. On that straight stream, there is still water droplets individually being pushed together and being sent out in that straight stream fashion. So we gotta look at how big are my water droplets? And the bigger my water droplet, the better it is. So let's use an analogy of water droplet sizes. If I look at a small little mustard seed, as small as it is, that's what I'm delivering from a fog pattern. Mustard seed size water droplets. But if I look at a big fat green or juicy red grape that's growing on a vine, those big fat green grapes are what I want to have coming from a straight stream or a smoothbore type nozzle. So the fatter the water droplet, the better. The smaller the water droplet, not so good. And we're going to see some numbers here. So again, through science, this is a little old from 1992, but it's still relevant because we still have the same fire behavior that's taking place back then we see today as far as our modern fuel loads and the kind of nozzles we're using. Mustard seed size, which is like 0.35 millimeters in diameter from a fog nozzle. The result was when introduced into that 1,000 to 2,000 degree environment, 75% of that water evaporated at the ceiling and became what? Became steam. Only 12.5% fell to the floor, and 12.5% got caught in the thermal, which means it just went into the thermal heat and didn't do anything, just kind of hung out there and did nothing. So nothing was really accomplished at all using that little mustard seed style or size of water droplet. Why do I want water to fall to the floor? I want water to rain down on the floor to cool the surface that I'm working on. It also tells me if I have water going up to my ceiling to cool off the ceiling and the walls, when the water rains down, it means I'm actually cooling the upper temperature because now that water is not becoming steam, it's actually staying water and raining down on the floor, helping to cool off the floor as well. So it's doing two things for me. Okay, 1 millimeter size, right? So not that big, not that fat yet, but a little bigger. 1 millimeter size smoothbore or straight stream water droplet. You had 40% evaporation at the ceiling. You had 55% of that water falling to the floor, and only 5% was caught in that thermal column of heat. Just looking at those two sizes of water droplets, you're seeing a stark difference in what the water is doing for you in terms of reducing temperature, extinguishing fire, and making the environment better for you and the occupants. And obviously, the second one is the better one. The bigger the water droplet, the more work, the better work is being performed to achieve the goal of suppressing fire. Okay, so another thing here you're seeing in terms of that water droplet, how much temperature can it absorb and reduce overall in the first 2 minutes? Well, the smaller 0.33 millimeter only reduced it by 135 degrees Fahrenheit, whereas the bigger water droplet, the 0.78 millimeter, reduced the temperature by almost 400. Again, the bigger water droplet size, it's able to do its job of dropping the temperature as we need to exponentially. So if it was a bigger water droplet, 1.5 millimeters in diameter, it would be even much more of a temperature reduction than the 0.33 millimeter one. Okay, so I'm just gonna throw some numbers, a bit more. Let's go for the first one, right? 0.8 millimeter, almost half evaporates, half falls to the floor. You have 4% lost in that convection. Let's go right to the 2 millimeter. That's a real fat, juicy green grape. 20% evaporation, 80% of the water goes up to the ceiling, hits the walls and ceiling, and falls on the floor, and almost 0% is wasted. Just looking at the first one and the last one, which one would you want to have leaving your nozzle to fight the fire you're facing? I know for me, my hand goes up and I'm saying, I want number 3. Give me the fat green grape. Give me that 2 millimeter water droplet size, because with that larger size of water, I am doing a lot of work in dropping that temperature from 2000 and I'm bringing it right down to almost nothing. That's what I want to have happen. And that's hopefully what your goal should be too, because by doing that, you're going to make the environment easier to work in. You're going to make it safer for the occupant, and it's going to allow you to knock that fire down or suppress that fire very, very quickly as compared to using a fog pattern or delivering not as much water and the fire getting the upper hand and overtaking you. All right, so we do have that temperature reduction. When I have water falling on the floor, okay, we used that term last week, heat flux. And you see the abbreviation of HRR, that refers to my heat release rate. That's the amount of energy production being produced from the fire. That's that megawatts. So when I have the megawatts of energy production, I have the heat flux on the floor from the radiant heat. I have to have raining down from the ceiling minimum of 84 GPMs to absorb that 2 megawatts of energy production in that particular small space. So why does this count? Why is this important for us to know? Because you need to know your nozzles. You need to know your branch and your lines, your pumping ability. When I am delivering water, how much water am I actually flowing and delivering from my nozzle? Is it enough to combat the heat release rates that are found within that structure? Is it enough to be able to have that water go into that superheated environment, hit the ceiling, hit the walls, and also rain down on the floor enough to drop the temperature everywhere and bring that reduction down so it's easier for me to work and easier for the occupant to survive should they be in a space next door to us? Am I achieving those goals? If I'm not, what do I need to do to change something so that we can? If we are, then good stuff. Keep pushing forward and keep ensuring you are continually meeting those proper flow rates to be able to um, knock down that fire there. So I've come to the end of our little lesson here, and I hope that looking at fire flows and water delivery, that even though there's a lot of numbers being thrown at you today, I don't want you to be too confused by, this number and that number. I want you to focus on the most important thing, which is this right here. Okay. As I mentioned, this is the key takeaway right here. Your water that you're delivering has to be sufficient in volume, right pressure, and distance and reach and pattern, which is a straight stream, always a straight stream for anything interior. Because if I do, then I'm going to be meeting the 5 ways that water helps me to achieve extinguishment, which is the unaffected fuel, fuel surfaces, the flame, the hot smoke or black fire, and the hot surfaces of which I'm working on and within that structure itself. So look at these 5 points, and then think to yourself, big, fat, green, juicy grapes. That's what I want delivered. I don't want mustard seed style water that's going to cause more harm and more steam conversion than with a big fat green juicy grape. All right. I do have a bit of time here, so if there are any questions, if you want to write them in there or ask real quick, I can do my best to answer your questions before I take off here before 10, my time.
Excellent. Thank you, Mark. The floor is open for questions. If you've got a question for Mark, you can drop a question into the chat. You could use the raise hand feature, or you could just go ahead and unmute yourself and ask your question. I like these trainings where we get into the more technical aspect of firefighting, right? Because a lot of times we kind of simplify it into, you put water on the fire and the fire goes out. But as we begin to educate ourselves and look at the research that Mark's talking about, we start to learn that there's a whole lot more to it than just that. And when we apply that, then it makes things better for us. It makes things better for the people inside the buildings that we're trying to rescue. It's really cool when we get into this sort of take the next step forward, right, in our education of how fire works. If you've got any questions, drop your questions into the chat. You could use the raise hand, or you can just unmute yourself. got a couple more minutes here with Mark if you've got any questions about anything that we learned this week or last week in this sort of two-part series.
Well, it sounds to me like everybody got it, which is perfect because I hope you did get it. So, on that note, I'm going to say thank you for your time. I do appreciate your time this morning or this afternoon. And if you do think of a question later on this week when you're kind of maybe rethinking or reviewing what you've seen or heard, don't be afraid to email that to Africa Fire Mission, and they will get that question or message to me, and then I'll do my best to reply back and get you the information you're looking for. All right. But on that note, I got to run to my next meeting, so I bid you all farewell and see you guys hopefully down the road in the future. Thank you.
Thanks, Mark. Appreciate you. All right, and thank you to everyone else for joining us for today's training, using your time, which is valuable, using your bundles and your network to be with us. We don't take that for granted. If you've found this information useful and you think that there's other people that might benefit from these trainings, be sure to share those registration links. We have plenty of seats available here in our training class. You can find more training resources available on our website, www.africafiremission.org. And hit the resources tab. There's a whole bunch of great information. There's training materials. There's information about fire safety assessments, all sorts of good stuff. I encourage you to go check that out. All of those are free resources that are available that we provide to try to help you do your jobs better and better serve your community. At this point in time, we're going to transition over into our tea time. So let me just thank you all, and I hope to see you all again next week.